Hello everyone, I'm Shihao from Penn State University. Welcome to my talk. In this talk, I will present our work Who Goes First, detecting Go Concurrency Bugs via Message Reordering. This is a joint work with Ziheng, Yu, my advisors Linhai, and Hong. As a young programming language, Go has already been used in many famous applications, including Docker, Kubernetes, and many others. Go is designed for efficient and reliable concurrent programming. For this purpose, Go provides lightweight threads called Go routines, and also advocates using channels to explicitly pass messages for thread communication, with the belief that message passing is less error-prone than the shared memory. Unfortunately, there are still many concurrency bugs in Go programs. For example, many concurrency bugs are found in Docker. Moreover, channels may be more error-prone than mutex. For example, a recent empirical study reports that 36% more blocking bugs are caused by misuse of channels. Let me show you a concurrency bug in Docker. The parent routine makes an indirect function call. The calling function creates two unbuffered channels and returns the two channels to the caller. Moreover, the callee creates a child routine. The child routine first calls a function, then it depends on the return value to send a message to one of the two created channels. In the meanwhile, the parent routine blocks at a select statement until it either receives a message from files after 1 second or receives a message from one of the two returned channels. If the message from file comes earlier, the parent routine merely logs the timeout and then returns from the current function. After that, no other routines have references to the two returned channels, and those no routines can receive messages from the two channels anymore. Both of the two channels are unbuffered. A sending operation on them does not proceed until another routine pulls a message from them. Therefore, in this scenario, the child routine blocks at one of the sending operations endlessly, causing a blocking bug. Unfortunately, no existing techniques can effectively detect channel-related bugs similar to this one for three reasons. First, concurrency bug detection techniques designed for traditional programming languages only monitor shared memory access and shared memory primitives. They do not consider and analyze channel operations. Second, existing static techniques designed for Go cannot resolve complex indirect function call. Third, existing dynamic techniques for Go merely report triggered concurrency bugs, and then they cannot increase the chance of exposing concurrency bugs. We propose to build a dynamic technique to detect channel-related bugs in Go programs to avoid fundamental limitation of static analysis. We focus on concurrent messages that are unique to the Go languages. Since the processing order of concurrent messages is non-deterministic, programmer must guarantee a Go program works well under all possible processing orders. However, due to huge number of possible orders, programmers may miss some orders and bring in channel-related bugs. Therefore, we decide to mutate the processing orders of concurrent messages in order to detect channel-related bugs. Although intuitions are straightforward, we need to tackle three challenges to build a practical tool. First, how to identify concurrent messages. Without process information about concurrent messages, we may waste our efforts on messages with an existing happens before relation. Second, a Go program may have a tremendous number of possible message orders. How can we identify and prioritize orders more likely to trigger bugs? Third, when a channel-related bug is triggered, how can we effectively capture the bug? We built a tool named GFuzz to effectively detect channel-related concurrency bugs in Go programs. GFuzz leverages the select statements to identify concurrent messages, applies the fuzzing to pinpoint and prioritize suspicious orders, and contains a novel sanitizer to capture triggered bugs. We conduct thorough experiments to evaluate GFuzz. In total, GFuzz detects 184 previous unknown bugs in famous Go open source software. We report all the bugs to the programmers. Programmers have already confirmed 124 bugs as real bugs and fixed 67 of them based on our reporting. We compare GFuzz with the state-of-the-art and it can detect significantly more bugs. This is the outline of my talk. I've finished the introduction part. Now let's look at how GFuzz identifies concurrent messages and enforces their processing orders. If two channel operations do not have a happens before relation, we consider they are concurrent channel operations and their processed messages are concurrent messages. It is challenging to determine whether any two channel operations are concurrent, since there are too many synchronization operations in a Go program and it is difficult to analyze their interactions. GFuzz focuses on select statements, which allow one coroutine to wait for multiple channel operations. This semantics indicates that the channel operation of the same select can happen simultaneously. Go programs commonly use selects, and those GFuzz can pinpoint numerous concurrent channel operations. We use a sequence of selected case to represent the processing order of concurrent messages. We statically assign a unique ID for each select and allocate a local index for each distinct case of a select. A concurrent message order can be represented with a sequence of tuples. For each tuple, its first element represents the select ID, second element represents the number of cases in the select, and the last element represents the local index of a selected case. For example, if we assume the ID of the select is 0, and one program run goes over the select twice and choose the second cases for the two executions, then the order can be encoded like this. GFuzz conducts code transformation to enforce a given order. GFuzz replaces each select statement with a switch statement. Function fetchOrder decides which cases to prioritize for this select based on the input order. For a select with n cases, we will replace it with a switch with n cases and the default clause. The ith case of the switch is to prioritize the ith concurrent messages waited for the select. The default is used when the order is specified for the select. To prioritize the ith message, we implement the body of the ith switch case as a select with two cases. The first case is the same as the ith select case, the same channel operation and the same body. The second one is a timer with a period t, and the body is the same as the original select. After the transformation, the ith message is prioritized for selection with the t period. If the message does not come before the timeout, the execution forks back to the original select, and GFuzz leaves the program to choose any message. We design the timer to avoid introducing false deadlocks, which cannot happen in real executions. Here we show the whole switch for the select. Next, I will discuss how GFuzz identifies and prioritizes suspicious orders. GFuzz applies the fuzzing method to continuously identify suspicious message orders and detect bugs. Specifically, GFuzz maintains a queue for exercised orders. It sequentially fetches the orders from the queue and mutates each of them to generate new orders. Then, GFuzz forces the test program to handle concurrent messages in each new order to detect bugs. At the same time, GFuzz collects the runtime feedback to decide whether an exercised order is interesting enough for further exploration. If so, GFuzz adds the exercised order to the order queue. We consider an exercised order is interesting if it triggers a new interleavings of channel operations and reaches a new channel state, such as a new channel creation, a new channel closing, or a new maximum fullness of a buffer channels. We do not devote equal effort to each exercised order. Instead, we compute the score for each order using this formula, which considers the trigger channel interleavings, the number of distinct channels created, the number of distinct channels closed, and the sum of maximum channel fullness. GFuzz generates more new orders for an order with a higher score. Next, let's discuss how to detect triggered concurrency bugs. Our sanitizer focuses on detecting channel-related blocking bugs, because Go runtime can capture channel-related non-blocking bugs, such as sending a message to a closed channel or closing an already closed channel. We hybridize two methods to dynamically track the runtime information. One is conduct source-to-source instrumentation. The second one is to modify the Go runtime. GFuzz dynamically maintains two data structures and leverages their contents to detect blocking bugs. Go info records which channels a coroutine can refer to. Chain info tracks which coroutine holds a reference to a channel. We update the contents of the two data structures when a coroutine gains or loses a channel reference. Let's take a look at previous bug example. When the parent coroutine creates the two channels, GFuzz updates the two data structure to show that the parent coroutine gains a reference to a channel CH and a channel LCH. Later, when the child coroutine is created, GFuzz updates the two data structures since the two channels are shared to the child coroutine. When the function parent returns, it loses the reference to the channel CH and LCH. GFuzz updates the two data structure to reflect this fact. Then, when the child coroutine conducts the sending operation on channel CH, GFuzz refers the two data structures and finds no other coroutines holds a reference to CH, and those no coroutines can unblock the child. Thus, GFuzz detects a bug. Next, I will discuss the implementation and evaluation. We implement GFuzz using Go 1.16. We use the SSA package to do the static analysis and AST package for source-to-source transformation. We also change the Go runtime to track some dynamic information. We evaluate GFuzz using recent versions of the following 7 famous open source software writing Go. All of them are popular. Based on GitHub stars, most of them are ranked in the top 20. All of the applications are large software with hundreds of thousands of lines of code. They can help confirm GFuzz capability to analyze large software. In total, GFuzz detects 184 previous unknown bugs. Among them, 170 are blocking bugs, where one coroutine blocks at the synchronization operation and cannot make process anymore. All these blocking bugs are detected by our sanitizer. 92 bugs render the buggy coroutine is blocked at the channel operation. 61 blocking bugs makes the buggy coroutine block at the select and wait for multiple channel operations. 17 bugs leaves a coroutine blocking when using a range to pull messages from a channel. The range keyword can drain a chain in a loop, and it keeps iterating the loop until the channel is closed. GFuzz also finds 14 non-blocking bugs. NBK stands for non-blocking bug. And 14 non-blocking bugs includes panic or fatal errors caused by new interface conversion, sending to a closed channel, or accessing an array using an out-of-bound index. GFuzz reports 12 false positives due to imprecise static analysis. We compare GFuzz with the state-of-the-art Go Concurrency Bug detector, Gcatch. Since fuzzing is a continuous process, we run GFuzz for 3 hours. While Gcatch is a static tool, we use it to analyze all packages that can be compiled. Overall, GFuzz detects 85 bugs in the first 3 hours. Gcatch detects 25 bugs. GFuzz detects significantly more bugs than Gcatch. Among the 25 bugs captured by Gcatch, GFuzz also detects 5 of them in the first 3 hours. GFuzz misses the remaining 20 bugs for 4 reasons. First, 6 more bugs can be detected by GFuzz, but they require longer fuzzing time. Second, 4 bugs cannot be triggered by message reordering. Third, for 8 bugs, we do not have test inputs to execute the buggy code. Fourth, 2 bugs are missed due to GFuzz implementation. Although GFuzz is effective, it does have limitations and cannot capture all Go concurrency bugs. For runtime overhead, average overhead of GFuzz is 3 times. For Sanitizer, the average overhead is around 30%, which is comparable with widely used sanitizer, such as address sanitizers and thread sanitizers. It is promising to adopt the sanitizer separately in another scenarios. To understand the merits of each GFuzz component, we run GFuzz on gRPC for 12 hours using 4 different settings. One setting is the full-featured version of GFuzz. The other 3 disable one component of GFuzz. The figure shows how the number of detected bugs changes over the execution time. X-axis is the execution time, and Y-axis is the number of unique bugs. First, the full-featured version of GFuzz detects 12 unique bugs. Second, if we disable the use of execution feedback, GFuzz detects 4 bugs in 12 hours. Third, if we disable the sanitizer, the Go runtime can help detect 3 bugs. Fourth, if we do not record the concurrent messages, GFuzz does not detect any bugs, and full-feature version detects most bugs, demonstrating the rationale of GFuzz component. As a conclusion, we built GFuzz, an effective dynamic Go concurrency bug detector, by reordering concurrent messages, using execution feedback to prioritize suspicious orders, and proposing a novel sanitizer to capture blocking bugs missed by the Go runtime. GFuzz detects 184 previous unknown bugs in famous Go applications. In the future, we plan to explore other methods to explore Go programs' execution states for more bugs, and design novel analysis algorithm to identify more concurrent messages. Here is our GitHub project link and its QR code, and my contact. Welcome to ask me or open issues at any time if you have any questions. Thank you. Any questions?